webinar. So today I'm going to talk about what I'm going to talk about is a technology from Zimmer and Peacock, which is really for the translation of how do I put it, academic research into, let's say, real products. So let me go forward fairly fast. So what we're interested in at ZP is actually, and I'll explain the problem in a minute. And the problem is that there's a lot of research going on, but it's not translating, let's say, into real products. And that's what I want to talk about today. So we're talking about creating impact, really from electrochemical sensing. So I've got some instruments in front of me. I also talk about biosensors, also talk about electroanalytical chemistry as well. So I'm going to jump straight into essentially a demo. So rather than doing a lot of talk, I just want to kind of basically show you something to start with. So in front of me, I have a screen printed electrode. I have a pipette and some ferricyanide here. And I just want to do a quick demonstration. So this is a very different type of instrument. You'll see the depths of this instrument shortly, but let me just do a quick experiment just to kind of put some context on this. Everything looks good. Just setting up the cyclovoltammetry, and I'll just do a quick cyclovoltammetry experiment. So that's running at the moment. It's going to go quite quick because I'm doing 100 millivolts per second, and I'm doing it on ferricyanide. And then when it's complete, you'll see that the data gets uploaded. So it now says upload complete. So I'll just hold my phone to you. This is very unusual kind of, let's say, potentiostat, because it only runs off the phone. So it's already smartphone enabled, but it's also cloud enabled as well, that actually all the data goes to the cloud. And so what I'll do is I'm just going to share my screen with you for a second, and then I will just navigate in and go to reports. I'll just do a quick refresh. And then the most recent report pops up. And then I can see my cyclovoltammetry that I just recorded up in this cloud system. So this is a very, say, powerful way of very quickly doing an electrochemical experiment. The fact that we're doing it on these kind of screen printed electrodes really eases the setup, can I say, of the instrument, because there's no cabling, etc. And the fact is there's never any question as to where the data is. Not only do I kind of know when the experiment was done and who did the experiment, because it's all saved in the cloud, I can actually see it. And you can then start from the cloud system. You can start sharing this data with colleagues and annotating it and downloading it and doing really what you wish to do with it. So let me change something, kind of slightly gear slightly, and just say, I just wanted to jump in and do that, because then the rest of this webinar will be in the context of this is what I'm leading back to, but there'll be another demonstration in a bit as well. So I just want to talk about the current situation in, let's say, academic research. I want to talk about point of care, point of need testing. Wherever you are globally, there's a decentralization of test, both in the food industry, the agricultural industry, and also in the healthcare industry. And when I say a decentralization of test, I just mean not sending samples to central laboratories, but actually testing samples in the field. And I think that screen printed electrodes and the kind of handheld instrument that I just demonstrated are exactly the kind of thing that people need in order to, get science out of the lab. I will talk about screen printed electrodes. I'll talk about reproducibility. I'll talk about this cloud enabled potentiostat. I'll talk about no more laptops. So you don't need to own a laptop in order to run this instrument. You can run it off an Android phone. You can run it off a iPhone. So as I'm running it off an Android phone today, so smartphones only. No menus. You're going to see shortly that in fact it uses the camera to scan QR codes, and it's the QR codes then that drive what the potentiostat does. And it really helps to translate academic research from TRL 3 to TRL 9. And then I'll do a summary. So current situation, this is a colleague of mine in the UK called Richard Compton. The current situation in academic researchers, this is the paper that Richard produced 2008. It has a title, it has an introduction, it has a, let's say, a mechanism of what he was trying to do in that paper. He has an experimental section, and he also then has raw signal and calibration. This is important because most papers, let's say in the electroanalytical space, end up delivering a raw signal and calibration. But with this new type of potentiostat that we've got at ZP, we're going to demonstrate to you that in fact it didn't have to finish with raw signal calibration. It could finish with an assay that you could generally give to doctors and nurses, for example. Otherwise, if you just leave your scientific papers with signal and calibration curves, then the science will never translate out of the lab, and that's the problem that we've been trying to fix. This is another paper by a guy called John Hart in UWE, the University of West of England in the UK, but it follows the same format. You know, we've got introduction, we've got electrodes, we've got raw signal, and we have a conclusion. And so many of these papers follow the same way. And then I was talking to some academics in the UK from the Metropolitan University of Manchester, and they were saying, look, there's 25,000 papers like this per annum. So there is no point in supporting, in some ways, further research that produces, 25,000 papers per annum. We really need to change this, and that's what we're doing at ZP. So rather than having all these papers just coming onto the shelves, we thought, okay, what is the problem here? The problem is that these papers are coming, but they're not translating into products and sort of leaving the lab. So I say here that I want to do a censored cloud demonstration. So what I'm going to do is I'm just going to change cameras for a second. I will stop sharing. Right, so this is the potentiostat. You just saw me do a quick demonstration of cyclovoltammetry. So I'm just going to pick up my phone for a second, and I'm just going to say, okay, a very common procedure or methodology that people like to use is square wave voltammetry. So if I scan the QR code that I have here for square wave voltammetry, it'll do square wave voltammetry. Let me just move along slightly. Now I can do, let me just go up slightly. Now I can do cyclovoltammetry. Let me do, go along a bit further. Now I can do impedance spectroscopy, open circuit potentiometry, and then amperometry. So you can see that there is no laptop required with all these menus, etc., to actually drive this device. But this device has something quite special. Because of the cloud, because it's enabled in the cloud, it can actually convert, for example, cyclovoltammetry into chili. So let me do that demonstration now. So what I'll do now is right. So now I've scanned the QR code and it's essentially in its chili mode. I'm just going to set this up so I can find the data in a short while. So I'll just put tab 4 so I can find that shortly. So let me take away this sensor, which I have done. Let me just bring in some of these actual chili sensors. Which I've done. Let me get a clean pipette tip, which I've done. And let me get a sample of chili. When I say a sample of chili, this is the product that I'm actually testing. So let me just put it onto here. Again, what's really great about electrochemistry as a science is you don't need much sample. And this is not the world's most super clean sample. You don't have to over prep these kind of samples. And then I'll just go continue. It's what I call a 1 in 10 dilution, and I hit start. And again, I can see the experiment progressing on my screen, but you'll get a kind of experience in a minute of actually what's, let's say, going on there. So it's gathering all the data, and then it's come back and it said something similar to last time. It said upload complete, but it's given the concentration. So it didn't come back with like raw signal. It's given the concentration. But let's go to the cloud now and have a quick look. What does this potentiostat do? So I come up to the cloud. I do a quick look in here. I will do a refresh. I can see the data, that tab 4. I'll click on that. Bang. And now actually what I had is I was saying, okay, well, it could do cyclovoltammetry, and it's done cyclovoltammetry. In fact, I've got some very, nice cyclovoltammetry up here, but it's processed the data. This cloud system has a data pipe built into it, which you can program for your assays. So if you own an instrument like this and you develop an assay, you can come into this cloud and you can change these values, and what we've done here is that we've done a low pass filter just in case the data was noisy. There's all sorts of filters that you could choose. We've flipped it around the y-axis. We've cropped the data between minus 200 millivolts and 900 millivolts. We've said show an extracted value, which is the peak height, and look for the peak height centered at 250 millivolts with a window of 300 millivolts, and fit it to this equation. And these are the gradient and intercept of that equation. And by the way, we did a 1 in 10 dilution. And when it's done all of that, what it will then end up doing is it finds the peak height, and using that algorithm, it's converted peak height into micromolar. And then if I just stop sharing and change cameras, and then it's delivered it to my phone. So you can really see the power that actually that was the conversion of cyclovoltammetry into a real number that somebody in the field could actually use. And this final step that's really holding back academic research, or holding it into the lab, because the final step is not being closed. So that's the sense of the cloud demo. So far, within a very short period, you've seen me do a quick cyclovoltammetry on some ferricyanide, and then a slightly longer demonstration on measuring the cyclovoltammetry of an organic molecule called capsaicin. But in that one, I actually also used the cloud to convert it into raw signal. And so Richard's paper that I brought up earlier on is actually one that we ended up translating into a product. But understand that if you have a new assay, and it's based on electrochemistry, and you own this, you've bought this technology off us, then you can actually use this technology to translate your assay into something that you could actually give to somebody outside of the lab and actually create real impact with it. And the fact that we've actually done that, if you ever look up Djuli sensing online, you'll find lots and lots of videos from Zimmer and Peacock, and it demonstrates that, in fact, we use this sensing or potentiostat in the lab to develop technologies and develop assays, but we also then use it as a product and in fact take electrochemical assays out of the lab and onto the market. Now, what I did was I took the screen printed electrode, I clipped it into the device, we put the 50 microliter sample onto it, I scanned the correct QR code. So you can see me going around scanning QR codes. So the software, let's say, resides actually on the phone, and we know what assay or what method to run, because in fact it uses a QR code reader. So that's how we essentially program it, and we run the assay. The raw signal comes back to the app, and we upload the app to the cloud. This is an important point, see, because how many people are sort of storing their data in different repositories, etc. In fact, if I look at this, of recent I've done 858 electrochemical experiments, and they're all saved up in this cloud system. So it's a really good way of knowing at any one time where your data actually is. So we sent the data up to the cloud, we pre-processed it, we processed it, and then we actually, in this particular case, the demo I just did, we actually sent a number back to the phone. And it's that data pipe at the end there. That's the really important, let's say, part of this. If you're interested, I'll send you a recording anyway of this, but you can actually install this software on your phone. If you scan this QR code off an Android phone, it will install the software. And if you've got an iPhone, you can scan this QR code. This is recorded, so you can watch this later on as well. Just to say that when you do install it, you set up an account, but when you're setting up that account, what you're actually doing is setting up an account on a cloud system called Djuli. So we've got the Sense It All app, which you can download off the Google Play Store, for example, or the Apple App Store. And when you set up that account, because you didn't have one, you're actually also setting up an account on a system called Djuli. So the app and the potentiostat, this is really the right way around of thinking about it. They're really data generating technologies. And then we go and store that data in a cloud system called Djuli, where we can again convert the data into meaningful concentrations, etc. Something that can be used by people, non-electrochemists out in the real world. And so I think we're the only people really at ZP that have this kind of holistic approach, which is, okay, let's make screen printed electrodes. And look, these screen printed electrodes don't look like your normal screen printed electrodes. They look like they're quite easy to handle. Let's make a elegant potentiostat, no cables, no slots. Slots are a disaster. That just clips in like that. And then let's really think about the app, and let's think about the cloud system. So it's the only really holistic system I would suggest on the market, where we've actually thought through, let's say, all the parts. And as I say, you can scan different QR codes, and you can do amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cyclic voltammetry, square wave voltammetry. And in particular, if you are interested in electroanalytical chemistry, then this is probably one of the best potentiostats for it, because it comes from a company that, if you look at our pedigree, we've been around for 10 years, and it's really all we do is biosensors, electrochemical sensors, and electroanalytical techniques. But then because of this data pipe capability in the Djuli Cloud, we can go from cyclic voltammetry to a chili concentration, for example. Now, the main problem that we've actually had to solve on this way is actually screen printed electrodes. So many people use screen printed electrodes. The problem is kind of this, that people expect screen printed electrodes to be low cost, and at ZP, if you buy them off ZP, they are low cost. But that expectation of low cost actually means, other than ZP, I think, just picking up one now, other than ZP, the problem is sometimes is quality. The quality is not met. There's a problem, I think, in the world of screen printed electrodes where there's the quality in terms of reproducibility is really a problem. And the problem is because there's more choice than demand. So what I mean by more choice than demand, if you want high quality, you often have to pay a high price. But in the world of science, where it's governments that are sometimes funding the R&D, there's just not the margins there. So people want a high quality, but they actually want to pay a low price. Now, the only way you can have a high quality and a low price is to have high volume manufacturing. This is where the problem comes from. So there's at least, I think I did a recent count, there's about at least 20 manufacturers of screen printed electrodes in this world. ZP is just one of them, so we're part of the problem. And people come and go in this market as well. Now, most of these manufacturers, and these are pictures from ZP, produce essentially too many screen printed electrodes, or they produce too much of a range of screen printed electrodes. And then you've also got academic groups producing their own screen printed electrodes. All this says that there's at least 10, if not 20, producers of screen printed electrodes in the world, with some of them producing at least 50 products. And ZP historically has also produced 50 products. But what that means is you've got something like 500 products, individual products available to the market. So if, under the keywords screen printed electrode, there's at least 500 products out there on the market. Now, the problem we've got here is there's only about 1 million experiments being done per annum on screen printed electrodes in academia. So you've got 1 million experiments being supplied by 500 products. That means that each product is only selling about 2,000 per year. I'm just going to hold this up. This is a sheet of 300 electrodes. This means that for a particular product line, I could potentially supply the entire globe with just 7 sheets. So that means that, in fact, 7 sheets would provide 2,100 screen printed electrodes. There's not enough. This is not high volume. This is not even low volume. What this is saying to you is there's an oversupply of many different types of screen printed electrodes to a very finite market, and that finite market therefore could be fed by very low volume manufacturing. Low volume manufacturing means that sensors are made, they're left on the shelves, they're aging, and actually it's only high volume that can actually drive both a low cost and a high quality. But if you don't have high volume manufacturing, which people don't, then you get the low cost, but you're actually getting low quality. And this is the problem. And I think nobody's really saying it apart from ZP. So there's a high price, but actually there's a low quality. At ZP, we're actually able to produce a high quality at a low price, but it's only through high volume manufacturing. So in fact, rather than offering like 50 screen printed electrodes now, we're able to say, okay, look, there's a limited range of screen printed electrodes. Please use these screen printed electrodes. Why? Because we produce them in high volume, which means that we can provide them at a low price and a high quality. So we're able to meet the prices of other people. But the problem that we're really trying to solve with this low price and high quality is actually reproducibility. So if you've got a background in electrochemistry, and I know that you have, people will often assess the quality of a screen printed electrode by looking at, does my peak height match the square root of my scan rate? Well, peak height versus square root of scan rate tells you more about the diffusion of that molecule, not so much about the electrode area. But people are very keen on doing this kind of Randall-Sevick type equation and say, well, there we are. That's the quality that demonstrates some quality of my screen printed electrodes. They also look at peak height, and I can understand that peak height is more indicative of not peak height, peak separation. What's my oxidation peak? What's my reduction peak? What's the difference in the potential between those two peaks? And they're obviously looking at about 59 millivolts per electron. So it shows a sort of Nernstian behavior. At low scan rates, we can get close to it, though I'm not saying we get 59 millivolts per electron. But what I am going to say, and we can get a one-to-one between oxidation and reduction, so we do tick some of these boxes. What I am going to say is the problem is not whether you show Nernstian behavior or Randall-Sevick type diffusion kinetics. The problem is whether your electrode is reproducible. If you watch any videos of ZP testing things like the Djuli sensor, you'll see that there's no calibration. You'll see that it's a simple assay. Simple assays are easier to commercialize. And the only reason that you could potentially have a greater probability of translation is if you didn't have to have calibration steps. Why do you have calibration steps? And it's often because actually these screen printed electrodes are not reproducible. And so you're having to do calibration on those sensors in the field to forgive the manufacturing. But at ZP, the screen printed electrodes are manufactured to a reproducible high quality, and therefore we do not need to calibrate. And if you have to calibrate, it's not going to lead to a low cost, easy to use point of need, point of care diagnostic. Now, how do we kind of ensure that reproducibility? We actually do test by electrochemistry, but we test by electrochemistry by scale. So there's probably like 12 or 13 electrodes being tested here, 13 electrodes being tested on this sheet 6, 13 electrodes being tested on sheet 18, 13 electrodes being tested on sheet 21. So you can see that we've really got a workflow set up where we test, we analyze, and actually we make sure that our standard deviations of, let's say, oxidation peak height are less than 10%. So 6% here, and then 5%, and then 6%, and then 6%, just to make sure that we're actually within, we're trying to make sure that our relative standard deviation is less than double digits. And in fact, these days now we can even get batches which are 3%. So we've got very, very good at reproducibility. But in order to get this kind of reproducibility, you can't just manufacture 2,100 electrodes one year and not do it again for the next year. We say to people, don't come to us and say, oh, I want this really bespoke screen printed electrode, because bespokeness means very small runs and production. And that actually then leads to it's not really being manufactured. They're just making them for you, but they're not manufactured. In order to be manufacturing, you need to be doing it day in, day out, every day, because then the team gets good at it. Your quality systems are all running. So how do we get reproducible electrodes? It's by high volume manufacturing. And that's also by just saying to people, look, don't go for bespoke electrodes. And actually, some of our electrodes, we got 501s or these hypervalue electrodes are very reproducible. And that reproducibility then means that when I do that demonstration for you, it works just full first time, because in fact the electrodes are of such high quality, and we would not be able to do that Djuli assay and have commercialized that Djuli assay unless we actually had worked out the reproducibility of the screen printed electrodes. So this is actually real data, for example, and here each color represents an actual concentration, and you can see that we have good relative standard deviations on those different concentrations. So that means less error bars, and less error bars means easier to commercialize that assay. The problem that we're really trying to solve here is that if you do an academic paper on let's say a large bulky potentiostat, then that paper will essentially get stuck at technology readiness level number 3. And then you will have commercial people who would like to commercialize it. And what we're saying is, rather than developing on large bulky potentiostats, please commercialize on the Sensi-All potentiostat from ZP, because then this valley between what you're doing and what's commercially viable is not such a big gap. And people say, oh, I need money in order to span this gap. I think actually they're just using the wrong instrument, because if you use and this is what you have demonstrated this morning in this demo so far, I've done cyclovoltammetry on this instrument, just like a classical electrochemistry experiment, and I've used exactly the same instrument to do a food test. And so it shows you that in fact you can do research on it, and you can use it as a proof of principle for getting that science out of the lab. So we call it Sensi-All. It really solves the problem of kind of commercialization and translation. So it's something we're particularly keen on at ZP. And we do allow people to create their own QR codes. So you don't have to be fixed by the QR codes that we provide. You can create your own QR codes and create, therefore, your own assays and even your own commercial route. So in summary, at ZP, if people want to be strategically aligned with us, they probably need to be on this platform, the Sensi-All potentiostat, using our screen printed electrodes. I mean, look at the elegance of the way this screen printed electrode just clicks into the device. No cables, no slots, and then that just clips up, and then it's made electrical contact. So to be aligned with us, you need to be on our potentiostats using our screen printed electrodes. Why would I say that? Because our screen printed electrodes are really reproducible. You've already seen this morning twice how I've just sent the data automatically to the cloud. So I'm never wondering where my data is. I can put the data through a data pipe in the cloud, and actually turn it into concentration. So it's not just a nice to have. In fact, it's no more laptops. So if you're trying to do a field deployed assay, you don't need any laptops for this. It's no menus. I was just using QR codes, and that your next paper you're going to do won't finish at technology readiness level number 3, because as long as you've got the calibration curve, you can put the calibration algorithm into our cloud, and it will turn your peak height, your area under curve, whatever you've got, into an actual concentration using your calibration. And that does help with commercialization. We also think this can play a big role in education as well as the research. So I want to say that I appreciate you coming this morning. I hope this gives you a deeper understanding that at ZP, we've set the entire business up really for the rapid translation of electrochemical assays into products. And this morning, I've just focused on point of care needs. But if you have any questions, then I would just say, look, don't hesitate to reach out to us. There's our contact details. Okay, thanks very much.